That's how far we got?
Yeah.
Okay. Then we're going to look for potential reactions here. So we look for potential reactions of silver. Or we look for patterns. Do you see some patterns here? We might try some patterns. One of the patterns we might see is like HCl and sodium nitrate. Maybe silver is just a spectator and HCl and sodium nitrate react, or maybe silver participates there somewhat. And so if you did HCl plus sodium nitrate, what would form? Yeah, nitric acid and sodium chloride. Then we look for a driving force for this. And we go, well, maybe it is the stronger acid, the weaker acid. We look at the acid chart. So we're going from HCl to nitric. So HCl to nitric with stronger acid to weaker acid, right? Wrong, yeah. And the reason was because of the, what do you call that? The effect? The leveling effect. Does everybody remember the leveling effect? Somebody summarize the leveling effect in one sentence. All these acids are going to have the same strength when mixed in water. Weak acids don't. When mixed in water, let's just do a quick aside for this. When mixed in water, what's pulling off the proton? Water. Water is going to be the base. Water is going to be the proton taker. So this is the acid. And so what we're going to end up with is hydronium and chloride. So if we start off with 0.1 moles of HCl per liter, then what's going to happen is all 0.1 moles will be stripped of the proton to form hydronium. And so what we're going to end up with is, we might start off with this initially, but by the end of this, we're going to have no HCl molecules with the proton intact. All the protons would have been stripped by water to form 0.1 moles per liter of hydronium and 0.1 moles per liter of chloride. This is strong acid. Strong acids, what's this reaction called? Hydrolysis. Strong acids hydrolyze water completely. I just put dashes here. The dashes here is because if I'm doing this in concentration, does the concentration of water change? No. Well, what about nitric acid? Nitric acid, yes, is a weaker acid. Nitric acid is a weaker acid, therefore water will have to struggle a little bit more to pull the proton off nitric acid. But does it have to struggle too much? No. In fact, HCl and nitric, those are low-hanging fruit. You heard that expression? Low-hanging fruit means it's no problem. It's going to pluck all of them. So what I end up with is, if I started off with 0.1 molar here initially, and all the hydrogens were intact and together, then all the nitric acids are going to lose that. And we're going to end up with 0.1 molar. Well, you know, if I have 0.1 molar hydronium, what's my pH? 0.1 is 10 to the minus 1 molar. 10 to the minus 1, what's my pH? 1. And so the pH of HCl is 1. What's the pH of HNO3? 1. They have the same pH. They have the same power of the hydrogen ion. Therefore, they're the same strength in water. This is the leveling effect. Whereas a weak acid, what did I call this? I called this the low-hanging fruit because water can easily pluck all the hydrogen seeds of the apples. But if I have a weak acid, then those are the high-hanging fruit. You know, it depends on how high it is. Water's not going to be able to pluck all the hydrogens off. So the stronger the weak acid is, the more hydrogens get plucked off, but not all of them. The weaker it is, well, that means those apples are very high. And so with weak acids, we're going to start seeing we aren't going to get 100% hydrolysis. We're going to get less than 100%. And the percent hydrolysis is going to depend on how strong the acid is. The stronger the acid, the greater the percentage. That's like, you know, if you're picking apples off the tree, you're going to get a higher percentage for the ones that are easier to remove than the ones that are very difficult. So, you know, the ones that are hanging at the top, you might just get a very small fraction of those. Does that make sense? So this is why I use the apple analogy, but you should try to remember it whatever way you can. Does sodium chloride precipitate? No, so there's no reaction, there's no driving force. So there's no reaction here, but maybe, you know what else I see? I see single replacement. Do you see single replacement? I see single replacement. Maybe it's a single replacement reaction happening. Ag plus HCl gives what? Or wait a minute, I'm missing a metathesis. Doesn't silver like chloride? I seem to remember that silver likes chloride. So this is metathesis too. So if silver likes chloride, then maybe I'm missing this because silver chloride should form a precipitate. Silver likes chloride. Does that look right? Yeah, it's not an I. This is silver metal. Silver metal is pretty unreactive. Like people make jewelry out of silver metal. People make coins out of silver metal. But do people make jewelry and coins out of silver ion? Like say, if you had some silver nitrate, no. What happens is that it stains everything. Silver nitrate, silver ions are a powerful oxidizer. It stains everything because it oxidizes everything, skin, eyes, whatever. So no, there's no metathesis. In other words, this is the Dr. Jekyll and Mr. Hyde. This is a Caccolici follows everything. One's very stable, silver. One's not so stable, silver ion. So what do we have? Do we have silver ion or silver? We got silver. So, but this looks like a single replacement. So silver plus HCl yields what? Single replacement, the advantage is it's so simple. It's going to yield A plus BX yields AX plus B. So it's going to be silver chloride plus hydrogen gas. To balance this, I'll need 1/2 hydrogen, or I could just double everything. Let's just double everything. Make that easier, except for hydrogen. Hey, is the driving force precipitation silver chloride? No. Why not? Why is the driving force okay for some but not okay for others? Okay, that's one reason, but there's a more important reason for that. You would have been perfectly okay if you said that for metathesis. You know, we start off with a solid, we end up with a solid, so we're sacrificing one precipitate for another precipitate. But this is not metathesis. For metathesis, we look for precipitation. But for redox, do we look for precipitation? No, we don't. We don't care if a precipitate forms, and we don't care if it's more stable or less stable than the other. Because precipitation is not significant compared to this. So in single replacement, what do we look for? We look for activity. You guys remember the activity series? What's at the top? At the top of the activity series is lithium, but we don't even need the activity series because we should be able to figure this one out. Which one's more active? Silver or hydrogen? So if you wanted to fill your treasure chest, would you fill it with silver coins or would you fill it with hydrogen gas? You'd fill it with silver coins because silver is going to be a lot more stable, less active. So we're going from less active to more active. Hydrogen is much more reactive, more active. Is that driving force? No, so we don't care about precipitation. We don't care about gas formation. Yes, hydrogen's a gas, but do we care about gas formation or precipitation? No. Why? Because this is a redox reaction. This is why I divide the reactions into different types. The different types are based on driving force. If you go back to the original. So all redox reactions have the same driving force. Make it easier. Rather than combination, not all combinations have the same driving force. Some combinations are redox, some combinations are acid-base, some combinations are metathesis. You have 3 different driving forces for 3 different types of combination reactions. And so that's why I separated it this way. Well, anyway, getting back to this, if we're going from less active to more active, then there's no reaction in our. But maybe between silver and sodium nitrate there might be a reaction. So what about that? So let's take a look at the reaction between silver and sodium nitrate. Silver solid plus sodium nitrate yields what? Silver nitrate and sodium metal. Do you need the activity series for this, or can you figure it out? If you had a treasure chest and you wanted something that would last, would you fill it with silver metal, or would you fill it with sodium metal? With silver. In fact, they had those 50-gallon drums filled with sodium metal that they dumped into Lake Lemoore, Washington. Do you think those drums still contain sodium metal? We went out there and scuba dove and looked for those drums. Do you think we'd find sodium metal still in there? No, but if those drums contain silver metal, then it'd be worth going up there and try to recover the silver. And so this isn't going to happen. We don't need the activity series. We should know enough chemistry to be able to figure out that this is going to be an R. And so we're done, right? We predicted no reaction for... Oh, actually, no, there's one more. Acid-base. Acid-base. Did we do acid-base yet? Yeah, okay, we did acid-base. How did we do acid-base? Did we inventory? No? Okay, yeah, if we look at this, we have the acid HCl. What's the base? Well, we probably should go back. Let me go back to the original PowerPoint of the acid base. Well, we have 3 basic types of acid-base reactions: Arrhenius, Bronsted, and Lewis. We're going to look at Bronsted. What are the steps involved in Bronsted? What's the first step? Inventory. So let's go ahead and inventory this. We're going to check for acid-base reactions. We did metathesis, we did redox, now we're doing acid-base. So if we inventory this, silver, that's just silver ions, right? Silver metals, silver ions? No, it's two different things. This is silver solid. What about HCl? What are the major species in HCl, hydrochloric acid? Sodium nitrate? Is that it? Is that it? And water. Probably the biggest presence in this will be the solvent water. All right, determine the strongest acid and the strongest base present. Silver, metal, acid, base, or neither? Neither. H plus, acid, base, or neither? H plus, acid, base, or neither? Well, maybe we need the chart. Take a look at this chart. H plus is AKA, also known as hydronium. So it's an acid. Makes sense. Chloride, acid, base, or neither? Well, chloride's here. Chloride's on the base side, but what do we know about these bases? Are these bases any good? Those bases are pretty worthless. But still, it's a base, so we'll just put it here. Maybe a little asterisk here. Terribly weak base. Sodium ions? Are sodium ions good proton donors, proton acceptors, or neither? Are sodium ions good proton donors? Good proton donors. Hydrogen donors. Do sodium atoms have a lot of hydrogen atoms they can give off? Yeah? Are sodium ions good proton acceptors? The NaH2 plus cation. Are they good proton acceptors? No. Are they good proton donors? No. And so sodium ions we call neither, neutral. Nitrate? It's a base. It's a terribly weak base, but it's better than what? Better than chloride, which isn't saying much. Water. It's both an acid and a base. Here we can see water as a base. It's not a very good base. Borderline bad base. That is just very weak. And then here we see water as an acid. Here, it's not a very strong acid. And so what we got to do is we got to select the strongest acid present. What's the strongest acid present? Hydrogen ion. What's the strongest base present? Chloride, nitrate, or water? Water. And so the most likely reaction to occur will be between hydrogen ions and water. If hydrogen ions react with water, what forms? Well, we're going to have 3 hydrogens, positive charge, hydronium. But, you know, this is pretty much a non-reaction, because what did I say H plus really is? Hydronium. So this is nothing new. And so basically we got no reaction, because I said that H plus is too unstable. Why is it too unstable to exist alone? H plus is too unstable to exist alone because size. Yes, incredibly small size. But you know, it's a hassle writing everything as hydronium, so we just still retain the H plus. So this is pretty much a non-reaction here. So we got no metathesis, no redox, no acid base. Are we done? Are we done? No, we're not done. There is a reaction that occurs here. And I have a more powerful technique than the single replacement method. What is it? The chart method. So let's go ahead and use the chart method. Maybe we could figure out. In fact, we didn't even have to do the single replacement. We could have skipped the single replacement and just replaced it with the chart method because the chart method is more powerful. So what's the chart method? From chapter 19, this is the chart method as explained by our book. Our book goes from strong oxidized, strong reducers to weak oxidized, weak reducers. It just talks about that. And then we have the chart. Then we have the chart method. This is the chart method that's presented by the book. Write the net ionic equation for the redox reaction between cobalt 2 ion and metallic silver. So basically the book is just saying figure it out by you looking at the chart. You know, they aren't giving you steps. So you got to figure it out using the chart. Well, you got to figure out the steps to do. So what we're going to do, though, is we're going to break it up into steps. These steps were earlier PowerPoint. What are the steps? And the steps are very similar. First step is inventory, similar to acid base. If we inventory it, we know we have silver solid, H plus, Cl minus, Na plus, NO3 minus, and water. But rather than labeling these acids and bases, we're going to label these as reducing agents and oxidizing agents. So let's take a look at the chart now. All right, silver metal. Oxidizer, reducer, or neither? Reducer. H plus, oxidizer, reducer, or neither? Plus. Oxidizer. Cl minus. Cl minus, reducer. Na plus. Oxidizer. Nitrate. It's an oxidizer, but you know, I'm missing something. Of nitrate, I need 4 H plus. Well, in this case, I have nitrate and I have H plus over here. But do I have 4 H pluses? And the answer is yes, I do. Well, how do I? This 4, does it mean I need 4 pounds of H plus? Does it mean I need 4 gallons of H plus? what does this 4 mean? This 4 means for every one of these, I need 4 of these. So it doesn't matter, you know, I might not react all the nitrate. It depends on what the limiting reagent is. And so as long as I have H plus and nitrate present, you know, the ratios are going to not always be perfect. You know, ratios aren't always perfect. That's why we have limiting reagents and excess reagent problems. If the ratios were always perfect, that is stoichiometric each time, then we'd never have to do a limiting reagent, excess reagent problem in our life. But it's not that way because, you know, sometimes you get a little extra, sometimes you don't get enough. We know what the perfect ratio is. The perfect ratio is 1 to 4. But what might happen would be I don't have enough nitrate or I don't have enough H plus, so not all of it reacts, but whatever does react will react in the right ratio. And so this is what I need. You know, I might have too much H plus, I might have too little. Depends on the concentration. And so this might be 6 molar HCl and 1 molar nitrate. If this is 6 molar HCl and 1 molar nitrate, then I have plenty. However, if this is 1 molar HCl and 6 molar nitrate, then I don't have enough, but still it's going to react in the right ratio. And so nitrate and H plus, that's my oxidizer. So I'm going to put a bar connecting these two because they're going to work together. And that will be my oxidizing agent here. These two. How about water? What's water? Is water an oxidizing agent or reducing agent or what is it? Well, here it is. Water. Do I use this one? I can. Why? Sulfur dioxide. Do I have any sulfur dioxide? And so in this case, I could use the nitrate because there was H plus. Where did that H plus come from? It came from HCl. I could dump in lots of HCl or a little bit. It depends on how careful I want to be. Here's some water. Use that? Here's water here. Should I use that? Yeah? No. Why? I'm not going to use this water. You know which water I'm going to use? I'm going to use this water. What's the difference between this water and this water? It's 2H2O liquid, 2H2O liquid. I'm going to use this water. Why is that? It's stronger. That's what I said a long time ago. I said it's stronger. If I use the stronger one, then why have the weak one? Can somebody explain why we have the weak one there? If I'm going to use the stronger water? And what makes one water stronger than the other? Isn't water water? How can you tell the difference? I want the strong water, I don't want the weak water. Well, here you go, 2H2O liquids. There's your strong water. I'll keep the 2H2O liquids, the weak water. What's the difference between the strong water and the weak water? Why do we have both? Isn't water just water? And what would you tell them? Yes. The reason why we have two waters here is not because of the reducing agent, it's because two different oxidizing agents produce the same product, water. This oxidizing agent, oxygen, produces water. This oxidizing agent, hydrogen peroxide, produces water. So both of these produce the same product, but the oxidizers aren't the same. Therefore, that's the reason we have a difference. And so oxygen is more stable than hydrogen peroxide, so this is a better water to use, stronger water. So water is going to, well, not an oxidant, it's a reducing agent, sorry. On the left side is reducing, right side is reducing agent. So water is just a reducing agent, or can water be an oxidizing agent too? Water can be an oxidizing agent too. In fact, water is at the bottom of the list. See this? Water is at the bottom of the list, which means water is the strongest or the weakest oxidizing agent on the chart. Is water the strongest oxidizing agent? Okay, if it's not the strongest, it must be the weakest. Is it the weakest? No, then what is it? It's out of place. That's what it is. Where does it belong? And so this is the only time you're going to use these numbers in this class, right? Position the water. Otherwise, we aren't going to use those. Yeah. Is this stuff sounding familiar? You know, we talked about a long time ago. But, do you remember it? Or not at all? All right, what's the strongest oxidizing agent present? So we want the strongest oxidizing agent when we have 1, 2, 3, 4 to choose from. So we'll start off with the strongest oxidizing agent, fluorine, and then work our way down. Nothing there yet. Here we go. So the first of the 4 oxidizing agents I did is nitrate and H+. So nitrate and H+, that's my strongest oxidizer. Is this one up here. What's the strongest reducer? I have 3 to choose from: silver, chloride, and water. So the strongest reducer, silver, chloride, and water. Here's lithium. Work our way up. Silver, chloride, or water? Water. Yes? Here's silver. Yes? Strongest? Yes, the water we're supposed to use is up here, chloride's way up there. So silver is going to be the strongest reducing agent here. Nitrate and H+ is the strongest oxidizing agent. So what's next here? The next step would be to combine the strongest oxidizing agent, half reaction, with the strongest reducing agent, half reaction. The half reactions we just copied from the chart. So I'll copy the nitrate here. I'm just going to copy it as it's written. Nitrate plus 4H plus 3 electrons yields NO gas plus 2 H2O liquids. And that's the silver, or actually that's not silver, that's nitrate, and then silver. If I look at silver, I'm going to have to reverse this one, because silver here is the product. We want to make silver the reactant and move these to the product. I'm just going to flip it. So silver solid goes to silver ion plus an electron. I need to combine these half reactions such that the electrons lost equals electrons gained. That is, over here I gain 3 electrons, something has to lose 3 electrons. Well, that's going to be silver, but silver here only loses 1. Well, that's an easy fix. We'll just triple it. So if we triple this second reaction, then we'll get 3 electrons lost and 3 electrons gained from the first reaction. And then we'll just combine these. So we'll end up with nitrate plus 4H plus. Now, the 3 electrons here will cancel out with 3 times 1, 3 electrons there. Plus 3 silver metals is going to yield NO gas plus 2 H2O liquid plus 3 silver ions. Simplify if necessary and determine if a driving force is present. So let's take a look if there's a driving force present, then simplify. That would be easier. To determine if there's a driving force present, what I do is I look at the half reactions. These are called half reactions here. And with the half reactions, we can get the conjugates pretty easily. Let me show you what I mean by that. Here. So what did we say nitrate in H plus is? Oxidizer or reducer? So that's our oxidizing agent. Oxidizing agents take electrons. If this is the oxidizing agent, then the products will be the reducing agent, the conjugate reducing agent. Because if I go consume electrons going forward, I have to give up electrons going reverse. And so NO and 2H2O liquids go backwards to produce electrons. It's a reducing agent. And so this is called the conjugate pair. I'll do the same thing here. Silver metal is our reducing agent. It's giving up electrons. But if we go backwards, then silver ion will be taking the electrons, so they'll be our oxidizing agent. So we can kind of think of these as going either way. That works. All right, so what we're going to do is we're going to label this one. The nitrate and the 4H plus, that's our oxidizing agent. The silver is our reducing agent. The NO and 2H2O, that's going to be our reducing agent. And the 3 silver ions, that will be our oxidizing agent going backwards. And then let's compare the strengths here. You know, silver ion versus nitric acid. Which one's stronger? So here's silver ion, here's nitrate and H plus, nitric acid. Which one's stronger? Nitrate and H plus. Not by much, but this is stronger oxidizing, this is weaker oxidizing. The reducers have to follow the same pattern. Silver metal versus NO, H2O. Which one's stronger, silver metal or NO? Silver metal, it's close to lithium. So this goes stronger to weaker. And so that checks out, we have a driving force here. That's good. Okay, what I'm doing here is this. The nitric acid is going to take 3 electrons. And so it needs 3 electrons for this reaction. Where's it going to get it? Well, it can get it from silver, but silver only gives up 1 electron. If silver only gives up 1, then an easy fix to that is to get 3 silvers. If I get 3 silvers, each giving up 1, then I have enough electrons for everybody. And so this is why I multiplied it by 3. In other words, I need to have 3 electrons gained and 3 electrons lost, always. The electrons must balance in the redox reaction. All right, so that is the reaction we expect here. Can I further simplify it? No. So that would be it. And so there is a reaction between those reagents there, those chemicals. Okay, what we're going to do Next are some more examples of redox reactions. Alright, the lab tomorrow is experiment 13. Experiment 13, we're doing a bunch of redox reactions, which is the same as chapter 19 stuff. And so this first section is the strength of oxides and agent. What's cobalt? Metal. Metals tend to be electron rich. And electron rich species are reducers or oxidizers? Metals tend to lose electrons. So we're going to use the same reducer. We're going to try to oxidize it using HCl. We'll try to oxidize it using copper 2 nitrate, cobalt 2 nitrate, silver nitrate, zinc nitrate, and nitric acid. We're going to try to oxidize it using those. If you look at it, we have two choices. One, we could do it via single replacement, or two, we could do it via the chart method. Which one's easier? Single replacement or the chart method? Single replacement, as long as you know what the exceptions are. What are the exceptions? Covered the exceptions months ago, but does somebody remember what the exceptions are for single replacement? All of them boil down to this. I use the director of the play. Does anybody remember the director of the play? You're the director of the play. The director gets to choose all the actors. But sometimes, you know, director might say, okay, you're going to play the role of this. But what if you say, I don't like that role, I don't want to play that role, I'm going to play a different role. And you refuse to play that role. That's what it boils down to. You're the director of the play, you're doing the single replacement play. What are the roles? Do you guys remember? A is, well, A plus BX. A plus BX. A is the not the oxidizing agent. A is the reducing agent. But what if who you chose to play A does not want to be the reducing agent? What if there's a much better reducing agent around? then it doesn't react as predicted, right? So we got to worry about that. Sometimes A isn't even a reducing agent. Sometimes A is a oxidizing agent. But what you did was you assigned the role of reducing agent to the wrong person. Let's say A is fluorine gas. If you say, okay, A is fluorine gas, A is supposed to be the reducing agent, is your reaction going to work very well? So do you guys remember the exceptions? The exceptions that we covered? Not at all? If you don't remember the exceptions, then probably the best thing is not to risk it. The best thing is just to say, okay, even though the chart method requires more work, I'm going to use the chart method because I don't want to miss anything. So we're going to skip that. Let's look at the first combination. Cobalt plus HCl. Okay, what do we do with the chart method here? We got cobalt. Cobalt is a metal. So what do you think? Oxidizing agent, reducing agent, or neither? Reducing agent. We have H plus, oxidizing agent. We have chloride, reducing agent. We have water. Water is both. Oxidizing agent, reducing agent. All right, which one is the strongest oxidizing agent present? Water versus H plus. Which one is a better oxidizer, water or H plus? H plus. What's the best reducing agent? Chloride, water, or cobalt? Cobalt. We didn't even have to look at the chart for this one. But you know what? Single replacement would have worked. Single replacement would have worked because we call A the reducing agent, we call B the oxidizing agent, and X is the spectator. It's not going to do anything. Single replacement would have worked here. Do you see that? Because everything is playing its assigned role. In fact, they want to play the assigned role because the best reducing agent got the role of reducer. And the best oxidizing agent got the role of oxidizer. It's just when you screw up. When do you screw up? You screw up when you give the role of oxidizer to the second best oxidizer or the third best oxidizer. You know? That's when it screws up. So, you know, single replacement, we're going to predict cobalt, chloride, and hydrogen gas. Here, it's the same thing. If I look at cobalt, unfortunately our chart doesn't have cobalt. So I'm just going to tell you, cobalt goes to cobalt 2 plus 2 electrons. I think our chart doesn't have cobalt. I'm sure. Our chart does not have cobalt. But anyway, cobalt has how many valence electrons? Cobalt's going to be an argon, 4s2, 3d1, 2, 3, 4, 5, 6, 7, 3d7. So it's 2 valence electrons. So cobalt 2 plus is pretty safe there. And then H plus, I'm going to have 2H plus 2 electrons yields H2 gas. And then I added, you see 2 electrons lost here, 2 electrons gained here. The electron's already balanced. I don't have to do anything. and then just combine these two. When I combine these two, I have cobalt solid plus 2H plus yields cobalt 2 plus H2 gas. We have here. And so we can do it two ways. If I do it single replacement, I'll have this, I'll balance it this way. If I do single replacement, I got to figure out the driving force. So what's more active? What would you rather have a treasure chest full of? Cobalt metal or hydrogen gas? Cobalt metal. So, you know, even though we don't have this on our activity series, we would think that this is less active. This is more active. You know, hydrogen is potentially explosive. However, cobalt metal is not like that. You know, actually powdered metal. So there's driving force here. This is called the CE. Then we have the IE and the NIE. When I do the chart method, I go straight to the NIE. And then I do the driving force a little differently. I look at the half reactions. This is my reducing agent. This is my conjugate oxidizing agent. This is my oxidizing agent. This would be my conjugate reducing agent. And so we do reducing agent, oxidizing agent, reducing agent here. And then we compare, you know, cobalt metal versus hydrogen. I think cobalt is more